And I'll stay here as long as I have to get to that. Okay, so the binomial distribution. Let's see. Let's get to question 15, then I'm going to hit the binomial. Hopefully that you guys will be able to hang around a little bit. Okay, number 15. You assign a graduate student to perform a survey involving a random phone calls. Based on previous surveys, only 20% of the phone calls respondents answer and complete. This is kind of like that 15, right? Kind of like the problems from that session. You assign. You need 10 or more complete the survey. Okay, so I'm going to get a fresh piece of paper here. Okay, I don't need this thing, so I'll get rid of it. Okay, so let me write down what we have, what the information that we have here is. I don't have to keep going back. Okay, so now we have the probability that you call some old geezer up and interrupt his dinner, and he completes that survey for a young, eager student like you. The probability is equal to 20% that they will talk to you on the phone and complete that survey, right? 80% of those geezers, well, let's see, probably 60% of them won't answer the phone. 20% of them will curse at you and hang up. And then you're left with about the 1 out of 5 that will actually be cooperative. You know, I'm an old geezer, I know that, so I know exactly how these people behave. So, let me get back here. Okay, so now you need to get 10 more surveys to complete your work, or the professor you're working with needs 10 more surveys, right? So you need to figure out, well, gee, what's the likelihood? I want to be 90% sure I complete this tonight. So the probability is equal to 20, right? So now you need 10 successes. The number of successes you need is 10. And we know that what we're usually dealing with here is the number of trials and the number of successes and the probability. So the way this would normally pan out, if we were going to do this in Excel, for instance, right, we would use Binomial Dist. Okay, again, this is another one of those functions where it's going to come up dot and give you 3 choices or something like that. You can just put a parentheses right there, and you can work with the default version of it. So the first thing it's going to ask you is the number of successes. This is very similar to those that 7 and 8 in that other question that we're talking about here. Okay, the number of successes, comma, the number of trials, the probability, and true or false, and cumulative, whether or not it's cumulative, true or false. You can't put a T or an F in there. You got to actually spell out true or false, right? So now, the way I would normally use this is, for instance, if you ask me, you do 100 you call up 100 people. What's the probability that you will get, let's say, 10 or more, 10 or few, I'm going to say 9 or fewer, right? 9 or fewer, because that would mean that I don't finish the survey that night. If I call up 100 people, 100 trials, what's the probability I'll get less than 10? Well, less than 10 is 9 people. So if I wanted to figure that out, I would use Binomial Dist, right? Number of successes 9, comma, number of trials 100, comma, 0.2 for the probability of success, any success on any individual. I would say true. And what would that give me? That would give me the probability that I would not get to 10, that I would get 9, 8, 7, 6, 5, or one person out of those 100. Let's do that right now. Let's pull up Excel. Give that a try right now. I'm going to zoom. I'm going to make it bigger. Okay, equals Binomial Dist. See, I can get away without that stuff there. Number of successes, 9. Now, you know why I don't use the 10? Because 10 would have been enough. I want a probability of not accomplishing this. So I'm doing 9 or less. Comma, number of trials is going to be 100. Comma, was it 0.2, I think, was the probability. Comma, true. Because I want probability of getting 9, 8, 7, 6, anything less than 9 out of 10 out of 100. And the probability of failing, if I make 100 phone calls, well, it's very, very low, right? It's less than 1%. It's 0.2%. So I'm almost certainly going to have at least 10 people if I make 100 phone calls. Now, the only problem is that I don't have time to make 100 phone calls. So I got to figure out what I want to be 90% sure. That's good enough. How many phone numbers should I take from the data bank and call tonight to be 90% sure that I'm going to complete this survey? Okay, so now, what did I do here again? What I did here was I'm going to put a number over here. I'm going to put this 100, the number of trials. Out here. That's the number of trials. Is in this column right here. Make it nice and even. Okay, and this is going to be the probability of getting 9 or fewer. Binomial dist. I'm going to do exactly the same thing. Parentheses, number of successes, 9 or fewer, comma, number of trials is going to be, I'm going to click in here instead of actually writing a number. I'm going to click enter, comma, 0.20, comma, and true. And I'm going to get the same result, right? Well, now, what if I try fewer trials, make fewer phone calls, like 90? Well, now the probability of failing is going to be a little less than 1%. How about if I make 80 phone calls? Probability of failing is going to be about 3%. See, now I could, if I wanted to, have gone in here and just changed that 100 to 80 and done it again and changed it to 70 and so on and so forth. But this is easier for me because this allows me to just change the number out here and recalculate it. So I'm going to try 75. Up 5% of the 5% of the time, I'll have 9 or fewer. I'll fail to get my 10%. My 10 surveys. 70. Up, I'm getting close. 68. It's a little bit more than I need. Let's try 69. Oh, no, I'm not. Okay. Oh, okay. If I go to 68, I will fail a little bit more than 10% of the time. In other words, I won't be 90% sure of being able to complete the 10 surveys that I need. So I'm going to stay at 69. Okay, at 69, I know the chances that I'll get 9 or fewer complete surveys is less than 10%, which means the probability of my completing 10 is going to be 91%. So that's the way I would approach this. Tell me something. Does that make sense to you? You guys comfortable with that? This is the kind of the most advanced version of this problem. Obviously, it would have been easier for me to just ask you simpler questions, but this was, towards the end of the homework, and it made it a little bit more challenging. I'm going to go now on to those questions that we just brought up that were about that exercise that Professor Rendina did. I'm going to open that up. I have it here also. And let me see here. Sample questions. Which one is it? Diagnostic practice. I think that's the one. Nope, that's not it. That's not it. Those are all sample questions. Hang on a second. I'll find it here. This is right here. Okay, let me blow this up. Okay. Now, questions that I got a couple of interested. Question number 2. Question number 3. Given the answers to question 1 and question 2, how many total rounds do you expect to play if you're going to tolerate only 20 losses? Okay, so now you got 20 tokens. Doesn't say anything about me winnings, right? Doesn't mean, like if you really were gambling. Let's say you were at what's the name of the place here? It's Aqueduct now. I think that's Resorts or something like that. Is that Resorts International or something like that? they have a casino out here. Let's say you're at the roulette table. I don't even know if they have a roulette table. Well, they got machines that are kind of like roulette tables. And you're betting a token. You got 20 tokens. You're betting them. Every once in a while, you're going to win. So you're going to have more tokens, less tokens. This doesn't work this way. This just, you have 20 tokens. You get to lose the 20 tokens no matter how many. Resort World Casino, thank you. Yeah, I knew there'd be some gamblers in this group. So you just get to lose those tokens. Whatever you win goes into your purse, and you walk away with it. You know that never happens. We know that. But that's the way this is intended to work. So right now you have a 75% chance of winning, but if you lose, you lose a token. You're willing to continue gambling until you use up all 20 of your tokens. Well, what's the probability of losing each round? Probability, if you got 75% chance of winning, the probability of losing is 0.25, right? Each round, your probability of losing is going to be 0.25. Let me narrow this so that you can see it. Oh, you can see it. I can't see it. Oh, okay. Oh, look, I did something here before, I guess. Well, maybe that was in there before. I must have filled that in. Okay, probability of losing each round, that's wrong, of losing a round is 0.25. I don't know where that came from. How many rounds can you afford to lose? You can lose up to 20 rounds, right? So now you can intuitively say to yourself, well, gee, if my chances of losing are 1 in 4, 25%, and I got 20 coins, well, that means that I can lose 80 rounds. I can play 80 rounds. Just think about it. If you're going to lose 20% of the time, you got 80, right? You're going to play 80 rounds. You're going to lose 25% of the time, point times 0.25. That's going to be your 20 tokens. You're going to lose, most of the time, you're going to lose in about 80 rounds on average. Won't happen every time. Sometimes you lose a little earlier. Sometimes you lose a little later. That's what the binomial distribution is all about. Okay, so you're going to lose it in about that amount of time. Okay, so now that we've decided that, we have some things that we might want to answer. What's the minimum number of rounds you could play with a 75% chance that you'll have enough tokens? Remember what we just did with that other distribution, binomial distribution? We're going to do the same thing here. Equals binom dis, parentheses. Okay, so what's the number of successes? Well, the number of successes is I can lose up to 20 coins, right? Okay, so now I lose up to 20 points. How many times can I play let's say I play 80 rounds, comma, number of trials is 80, comma, my probability of losing is 0.25, comma, and cumulative. I could lose up to 20. Up to 20 times. Say cumulative. So out of your 80 rounds, you lose 19, 18, up to 20. Same thing happened to Professor Rendina. I don't know what it is about this particular. I'm going to format this whole row. Good. Okay. 56% of the time, if you play 80 rounds, 56%, majority of the time, you will run out of, you'll lose your 20th coin. If you pay, you will have lost your 20th coin. You lose either 20, 19, 18, so you'll get to the 20th coin. 50%, 56% of the time, you will be able to lose up to that amount. So now, just like before, I said to myself, that's the probability that you will play 80 rounds and still have your 20th coin and lose your 20th coin by the 80th round, right? So there's a 44% chance you can continue to play a little bit more, right? That makes sense, right? Sometimes you'll get knocked out early, sometimes you get knocked out later, right? But there's a 56% chance you'll lose by the 80th round. You'll lose your 20 coins. It's more likely than not because that's the expected outcome. You should expect only to get your average outcome. You're only going to get to the 80th round. So now I'm going to say to myself, well, gee, let's say that 56% of the times I'll have enough tokens to get to 80, right? Not always, but that amount of time. Okay, so now I want to find the probability that how many times can I play that I'll have a 75% chance of not losing my coins until I get to that point. So I'm going to do the same thing here. Instead of going, I'm going to see if I can do this. I think if I just hit enter here, yeah, there you go. If I just hovered, I could go in here and change this. I could, the probability doesn't change. The number of losses I can sustain, the successes but what's the problem? If I only played to 70, would I still have my 20th coin? Can I be 70 instead of 56% sure of getting to that point? Can I be 70? Can I be 75% sure? One way I can do this is to just change this to a 70 and see what the probability of getting to. Oops, I messed that up. What's the probability? What do I do there now? I got to change this back to 0.25, I think it was. Man, it doesn't like me editing this way. Oh man, every time I touch something, it goes away. 70. Why is it doing that? Oh my goodness. 70. Binomial dist, 20, comma, 70. Oh, you know what? I know what it is. My tablet is leaning against something, and it thinks I'm pressing buttons. Sorry about that. Binomial dist. I'm going to hit escape and click in here and hover in here again. Here we go. Now, let's say I change this to 70, right? So now this will give me the probability of being able to get to 70, given that I have 20 coins that I can afford to lose. Probability of getting to 80 was 56%. What's the probability of getting to 70? Well, that's 80%. But I was looking for, I can take a few more rolls because I want to get to 75%, right? So I'm willing to take, I don't need that higher probability. So what I could do is just keep changing this number, or even better yet, I could put a number out here like 70, right? The one we just did. And I could tell it, instead of using 70 in here, use what's in this box so that I don't have to keep, see, it's the same thing. I don't have to keep recalculating. So now I can try, well, can I get to 72 with a 75%? Well, I can. Okay, what about 71? Well, now I'm up to 78%. How about 69? %. Did I go the wrong way there? 70. Okay, I can go higher. 72. I can go higher than that. 73. That's where I wanted to go. Oh, once I go to 73, if I have 73 rolls, I'm only 73. It just happens to be a coincidence. It's a similar number. There's only a 73% chance that I'll get to 73. That I'll get to 73 trials without using up that 20th coin. Okay, so really the answer to this would be 72. Now I have at least a 75% chance of getting to that point. Now, what is the number of rounds you could play to get with a 95% chance that you'll have a lot of tokens? So you can't, if you want a 95% chance of not losing that 20th coin, right, until that point, well, then you really got to cut down on the number of rolls. Let's try 65. Now you got 89% chance if you only you got 85. How about 60? Up there you are. 60. If you keep it down to 60 rolls, there's a 95% chance that you'll get to the 60th without losing your 20 tokens. Does that help at all? I mean, this is really kind of like a kind of odd way of looking at the binomial distribution, just to make sure we are trying to get to a target number that will give us, that will give us, to get to, well, the first question, the first one at 9%, what it was really asking you that you want a 90% chance of getting to a certain number of trials, right? Which means a 10% chance of not reaching that, right? So I was looking for anything under 10%. Yeah, the hard part is figuring this out. It's kind of like not the most intuitive thing in the world, right? But I think if you kind of look back at this, if you get a question like this and you look back at this solution, you can be able to say to yourself, well, let me see, what did I do here? Well, he asked me what I needed to get to make sure that I had a 95% chance of completing this task, right? So let's see, what number of trials would I have to be 95% certain that I wouldn't exceed 20? It's kind of like a little bit backwards from the one that we did, a little bit different than the one that we did before with the phone calls, right, and the surveys. Right, it's a little bit different from that one. That one, we were kind of like we wanted to make sure that we were able to get a certain number of successes. With this one, we want to make sure that we have that higher probability of reaching this point. Right. So when we clicked in here, we didn't change the number of successes. We only changed the number of trials. Right? And same thing on the other one. We changed the number of trials in order to figure out what the probability would be of accomplishing what we were trying to accomplish. Okay? And in the other one, what we're trying to accomplish is less than a 9% chance of not getting to that point. And on this one, we wanted to have a 75% or 95% chance of getting to that point. So I kind of used them a little bit differently. Okay, so hopefully you'll be able to go back over these two examples when I post them, and you'll be able to interpret them a little bit. Now, for those of you that can still hang around a little while, I just want to go over some of the diagnostic questions. Okay, we're not going to have time for the sample questions, but they are posted online with the answers. It's 2 documents in the sample stuff, the questions themselves and the questions with the answers. But I just want to go over these diagnostic problems, this particular document, for those of you who can hang around just a little bit longer. Okay, so a device measures blood pressure correctly, identifies 85% of hypertensive individuals, those with high blood pressure. It correctly identifies 85% of the people who have high blood pressure, this device, right? Well, that means its sensitivity is 85%. If you have the disease, it's 85% certain that it'll detect it when you have it. It incorrectly identifies 10% of normal people as being hypertensive. Oh, it makes a mistake on 10% of the people who are normal. That means it gets normal people right 90% of the time. Kind of like threw a little twist there, right? So it's specificity. The percentage of the time it correctly identifies people who are not hypertensive is 90%. It makes a mistake 10%. We're really interested in how often it gets it right. In both cases, sensitivity, specificity, we're interested in how often it gets it right. They told you how often it gets it wrong for people that don't have the disease. So you have to work backwards a little bit. That's a little bit of a twist, right? So the sensitivity is 85%. The specificity is 90%. Okay, assuming 20% of the population is hypertensive, this is what you would see. 1,000 people, you'd say 200 of them are hypertensive, 20% of the population, 800 are not. So the test would get these 200 people that have the disease, it would get it right 85% of the time. 85% of 200 is 170 people. It correctly identifies a positive test for 170 out of 200 people, 85%. Gets it wrong 30 on 30 people, right? The other 15%. Now, as far as the people who are not hypertensive, don't have the disease, they're in this column, right? Those people are 800 people in the population because it's 20 of the 1,000 people because 20% are hypertensive, 80% are not. 10% of those people, it gets wrong. That's where the 80 comes from. 90% of the people, 720, it gets right, our specificity, right? So if I add this all up, what's the sensitivity of this device? Well, like we said, it's 170 out of 200 or 85%. 170 over 200 is going to be 85%. What's the specificity? Well, it gets it right 720 times out of 800. So the specificity is 90%. If a patient tests positive, what's the probability they are hypertensive? Ah, that's interesting. Okay, patient tests positive What's the probability or they really have the disease, that they're really hypertensive? Kind of hard to highlight these charts. 250 people tested positive. 170 of them had the disease, 80 didn't. But you had 250 people out of 1,000 that tested positive in this population of 1,000 people. What's the probability that those 250 people, that any one of them has the disease? Well, let's see. Out of those 250 people, only 170 of those positives were people actually had the disease. 80 didn't have the disease. So the probability is 170 over 250. I think that's going to be, what is that, 68%? I think that's 68%, that one right there. That is called our positive predictive value. How reliable a positive test is, positive predictive value. It's 170, number of people who had the disease and tested positive, over the total number of people that tested positive, right, which is 250. If they test negative, what's the probability they're not hypertensive? That's a negative predictive value. Let's see how many people tested negative. 750 people tested negative, right? Out of those 750 people, 720 were really negative. So the negative predictive value for is 720 over 750, okay, which is going to be, I'm going to guess it's 96%. Am I right? 96%? I'm pretty sure that's what it is. Okay, so now, what is this called, this positive predictive value? This positive predictive value is called a conditional probability. Why is it called a conditional probability? So what we're saying is, what's the probability that you have the disease given that you have tested positive? We're only considering the top row. Okay, it's since we're only considering the top row, we're really focusing on just those people that have tested positive. So it's conditional. The condition, if you didn't test positive, you don't satisfy that condition, we're ignoring you. And how do we write that? Let me just go back to get some paper. If I have something available here. Yep. Okay. This will do. Yeah. The way I would indicate that is the probability of having the disease given that you tested positive. That's the positive predictive value. Okay, there's a lot of ways for us to get to that. The easiest way is to get to it using that table, by actually calculating it through that table. This is the number of people that tested positive. This is the number of people who actually had the disease. Right? Given that you tested positive, you're down to 250 people. What's the probability you have the disease? 170 people out of the 250. Right? That's our positive predictive value. Similarly, another way to calculate that is to use Bayes' theorem. And Bayes' theorem basically boils down to, when we really get down to it, if I can turn this off, okay, if I can get into this thing here, you can use this formula. If you know the sensitivity, sensitivity, the prevalence, and the specificity, and those three things we figured out, first three things we figured out. If you know those, you can plug it into this formula to figure out what the positive predictive value. Instead of A and B, you would have probability of disease, given that you tested positive. And you could, with a little bit of work, you could plug it in there and actually calculate that. Okay, and let me see if we got something else over here. So now, they redid this study with a population that had a lower prevalence of hypertension. There weren't as many people that were hypertense. Let's look at what happened here. Out of 1,000 people, if the population, if the prevalence of hypertension, of high blood pressure in the population is 4%, well, then out of 1,000 people, you'd expect about 40 of them to be hypertense, to have high blood pressure, right? Out of those, you know the test is right 80% of the time, so it would find 34, 80% of 40 is 34. 84% of the time, 34 people out of those 40 get it right. 6 out of those 40 would get it wrong. Similarly, with negative, you got 960 people that don't have it because only 4% prevalence, right? 90% of the time you get it right, that's 864. And the other times that we get it wrong. So now, because the prevalence is so low and there's so many people that are not hypertense, there's more people that are not hypertense, the 10% of the time that it gets it wrong in this population is going to go up. More people are going to be incorrectly diagnosed as being hypertense. Similarly, because the number of people in this population that have the disease is lower, then they're going to have fewer correct tests for positives. So now when you add these two together, you get 130 people that tested positive. But now when you calculate the positive predictive value, instead of being whatever it was before, I don't remember, 80% or whatever it was before, it's going to be 34 over 130, or I guess somewhere around 30%. I guess it must be 26% is probably the right answer. As the prevalence of the disease in the population goes down, the positive predictive value of the test goes way down also. Okay, and that's a problem because then you do all sorts of things based on assuming that they have the disease that you might otherwise not do. Okay, are you guys comfortable with that? Yes? Any other questions? I'll try and post this as quickly as I can. And hopefully that helped out a little bit. Like I said, you have 2 sets of sample questions and answers there that you should go back to and go over. And I'll be checking my email for the next couple of days. And I'm glad to help. And if you have any questions, again, if you put PH750 in the subject line, it'll make it almost certainly that I'll get to it, before the test, But otherwise, it's kind of hard to keep track of all these emails. Right? So give that a try. Okay, I'm sorry. Okay, Nicole, do you still have a question now? Or do you want to email me, or do you want to go over quickly now? Okay, which question was that? I'm hoping that you won't get kind of a really quirky kind of binomial distribution question. It'll be a little more direct than maybe this idea of doing this kind of like backwards calculation. Or at least if you do get that, it'll only be part of a binomial question that you get more straightforward one. Which question was that, Nicola? You're dealing with an old person here with a very bad memory. Oh, number 15. Oh, okay. Let me see. Number 15 was. Oh, that was my number 15. Okay, that was on the assignment. Let me go back to that. Assignment number 2 was that, or number 1? That was number 2. Yep, that was a binomial distribution. Okay, I'm going to go through binomial distribution quickly once more. You signed a graduate student performance survey. Blah, 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 blah. Okay, let me get Excel because I think that's going to be a better place to work on this. Let me get this out of the way. And I'll get a new document and blow it up. Okay, binomial distribution. Okay, I'm going to rephrase that question a little bit. Okay, let's see. I wonder if I can. No, I can't do that. There's a better way I can do this. I am going to rephrase this question and work through it in a couple of steps. Okay. Now let's blow this up. Okay. Yeah, that's a little confusing, right? That 0.09. Let me go over it again just quickly, and we'll see if this helps out. First thing I'm going to do is I'm going to rephrase the question just a little bit, make it a little simpler. You assign a perform. The graduate student perform a. I'm going to actually do this twice. I'm going to break it up into two questions. Okay, you assign a graduate student performance survey involving, based on previous service, 20% of the respondents answer and complete the survey. Okay, what's the probability if the student makes 60 phone calls, what's the probability that they will get 10 complete surveys? Okay, that's a little bit clearer, right? Makes some sense? See, you see how that's related? We're going to tell you that the number of trials is 60. They're going to make 60 phone calls, and the number of trials is going to be 60. Oh, let me click in there and add that word calls. Okay, so we want to know what's the probability that they'll get 10 completed surveys if 20% of the time the people are willing to complete the survey. Okay, so how are we going to figure that out? Well, we have everything we need. We have the probability of any individual that we call completing the survey, which is 0.2. We have the number of trials, which is 60, and we have what we want. We want to get at least 10 completed surveys. Okay, so let's go to Excel, equals binomial dist, parentheses, and the number of successes. We want 10 completed surveys. We want 10 surveys to be completed, comma, the number of trials is 60, comma, probability is 0.2, comma, and the, okay, now, a little bit of a problem here, okay? We want to know how likely it is we're going to get our 10 surveys, 10 or more surveys. If they call 60 people, get 11, that's good too. 12 is good too. 13. We don't want 9 surveys. We don't want 8 surveys. We don't want 7 surveys. We don't want 6 surveys, and so on and so forth. If I type in true here, it'll give me the probability that I will get 10 surveys, good, 9 surveys, not good, out of 60. That's not what I want. I want 10, 8 surveys, 7 surveys, 6. Those are all failures. I don't have enough surveys. So I'm going to put the number 9 in here. The reason why I'm putting the number 9 here is because I want to know the probability that if I call 60 people, that I will get 9 or fewer surveys completed. In other words, that I will fail and not get my 10 surveys. Does that make sense, Nicola? That's what that's going to give me when I do this calculation? I think we're okay there, right? I'm going to hit enter. And the probability of that happening is 21%. That means I got a 69% chance, 79% chance of getting my 10 surveys because the probability of getting 10 or more is going to be equal to 1 minus this probability. This is the probability of getting 9 or fewer. Okay, unfortunately, I can't tell it, give me the probability directly of getting 10 or more. Binomial distribution only works to the left, to the low end. Okay, but that's why I put in 9, because I didn't want to include 10, because this is the probability of failure, less than 10, and this is the probability of success, 10 or more. Okay, that's what those probabilities represent. Okay, so now I'm going to twist this around a little bit. I've got 78% chance of succeeding. It's almost 79% chance of succeeding and getting my 10 or more surveys if I do 60 phone calls, right? Well, it's really important that I get it done tonight, but I don't want to be up all night. I'm going to assign my students to make a certain number of phone calls I think I'm 90% certainty of getting it done tonight is okay for me. It's good enough for me, right? So now what I need to know is, what do I have to do to change this number to 90% chance of success of getting 10? Well, the way I do that, the way I need to do that, I messed that up again. The way I need to do that is to reduce this to the point where the chance of failure is less than 10%. Because I know if this is less than 10%, 1 minus that is always automatically going to be 90%. So I'm going to click in here, and I'm going to say to myself, I know if I increase the number of trials, that I will have a lower chance of failing. So if I change this, let's see, I had 21% chance of failing if I only made 60 phone calls, getting less than 10. Okay, if I change this to 65, I should have a less of a chance of failing. It should be less than 21%. And indeed it is, it's 13%. And that means that I have an 86% chance of succeeding. I'm getting closer, but I'm still not there yet. This has to be less than 10%. This has to be greater than 90% chance of getting 10 or more. So I'm going to click in here again, and I'm going to say, let's increase this to 70. And hit enter. Well, now here we are. I'm less than 10% chance of failing, more than 10% chance of succeeding, right? So this satisfies. If I do my 70 calls, I got a 90% chance that I will get. I have a 90% chance that I will get 10 or more completed surveys. In other words, I got an 8.5% chance that I'll get fewer than 10, and a 91% chance that I'll get more than 10, right? So I got better, but you want to know something? I might actually be able to do less and still be over 90%. So let me go back in here and change this to 69. See if I'm still over my 90%. Well, I'm still over 90%. Okay, let's try 68. Maybe I can make one less call. Oh, that won't do. I'm under 90% here. I'm over 10% here. I'm under 90. So I'm going to go back to what I had, my 69 calls. So I have to make 69 calls to be have less than 10% chance of getting 9 or fewer successes, completing surveys, in order to get a 90% chance of getting 10 or more, the rest of the possibilities. Okay, I hope that makes it a little bit clearer. Maybe you go back over it later on. The jump from the first part of that question to the second part of that question will make some sense. I know it's kind of like first time you look at binomial distribution, and especially this way that you use it in Excel, it can be very confusing. But trust me, doing in Excel is far superior to what the real math is, with all those exponents and combinatorials and so on and so forth. It's a lot more difficult to do it that way. Okay, guys, have a good afternoon and weekend, and best of luck on the test. I hope you guys all do very well on the test. And like I said, email if you got more questions.